Good morning. Welcome to the lecture series of VLSI technology with the subject code KEC 053 as per the AKTU syllabus scheme. This is a lecture 7 for this video lecture series, and the topic we are going to discuss today is the molecular beam epitaxy. So till now we have covered the classification of epitaxial system, that how this epitaxial process can be classified into three parts, that is liquid phase epitaxy, vapor phase epitaxy and molecular beam epitaxy. And we have already discussed that for silicon we generally prefer to have vapor phase epitaxy because the melting point of silicon is very high. So we cannot use liquid phase epitaxy for the silicon. So we generally prefer to have vapor phase epitaxy for the silicon. And MBE, molecular beam epitaxy, is a physical evaporation process where your substrate and the dopants are evaporated, then mixed, and then again it will be deposited on the wafer. So it is a physical evaporation process with no chemical reaction involved in this. So the basic difference between MBE and the another epitaxial system, we have seen that till now we have seen that one is there is no chemical reaction involved in case of MBE, but whereas in case of liquid phase epitaxy and vapor phase epitaxy there will be some chemical reactions involved. So if you compare these two epitaxial process, the very first major advantage for this molecular beam epitaxial process is it is carried out at a very at low temperature. The processing which is used to carry out the molecular beam epitaxy process is at low temperature, whereas the VPE is carried out at high temperature. Now because of the low temperature, the beauty of this low temperature processing is that the effect of auto doping can be minimized. In the last lecture series we have seen that because VPE is carried out at high temperature, the chances are the dopants which are present in the substrate, they may out diffuse and then it will be again reintroduced into the epitaxial layer. So it will affect the overall properties of the epitaxial layer. So auto doping problem that is present in the VPE, it is minimized in case of this molecular beam epitaxy. In case of molecular beam epitaxy is the one in which we have precise control of the doping because there is no chemical reaction involved in this. So in case of VPE there are some chemical chain reactions. From silicon tetrachloride to silane, there are some chain reactions. We have to control those chain reactions, but in case of MBE, no such chemical reactions are involved. So because it is a physical evaporation system, along with the silicon, a measured quantity of dopants are evaporated, right? Now we can control these dopant incorporation, which is very much precise in case of MBE. We can very precisely control the dopant quality as well as the quantity. Hence, the growth rate can also be controlled. So, you can achieve the growth rate as small as possible, that is 0.01 micrometer per minute. But in case of VPE, it was 1 micrometer per minute, 1 to 3 micrometer, right? And that is a very much high width in case of VLSI technology. So depending upon how thin or thick you want to grow the epitaxial layer, we can control the growth rate. So this 0.01 micrometer per minute, this states that this 100 Armstrong per minute. So with the advantages of VLSI technology, because we are going to reduce the size of all the dimensions, we have to reduce the size of all the dimensions so that we can accommodate more number of transistors on a chip. So the dimension of this epitaxial layer is also to be reduced. So to reduce the epitaxial layer, this molecular beam epitaxy is the most preferred choice. So in case of VPE, because of the fast growth rate, it is not possible to have thin epitaxial layer, because the growth process in case of VPE is very fast. So and the problem of auto doping is also there. So MBE, molecular beam epitaxy, eliminates both the problems. So now we can have a smaller growth as well as minimize the auto doping effect. So the problem, you can grow the problem with the growth of epitaxial layer, so and the auto doping problem, that both can be controlled now. So now we can have a better control over your epitaxial layer, and in case of MBE, no boundary layer or stagnant layer problem is there, right? So MBE is a very costly process. The only drawback is it is a very costly process. Some sophisticated equipments are required, and in overall India, only 3 to 4 molecular beam epitaxy system will be there. So in case of MBE, what is this MBE, molecular beam epitaxy? I have stated so many times that it is a physical evaporation process. The layer to be deposited, it can be of silicon or any other material which has to be evaporated. The evaporation is done under a very high vacuum condition to minimize the contamination problem. So a very high vacuum condition should be the first important point for this molecular beam epitaxy. There will be no collision, and so MBE is always done under vacuum condition. And silicon MBE particularly, it is carried out at 10 raised to the power minus 8 to 10 raised to the power minus 10 torr. The heart of the complete molecular beam epitaxial system is the ultra high vacuum pumping system. So once this ultra high vacuum condition is created, we must do the evaporation of the species, that is silicon and dopants. Okay, first we have to create the vacuum, and then high quality vacuum should be there, and then evaporation is carried out. Because we know that silicon, the melting point of silicon is very high, that is 1400 degrees C. So instead of thermal heating, electron gun is used to melt the silicon. Your electron beam will be targeted on the silicon, and then it is evaporated. So this is the diagram. This is the simplest diagram of the molecular beam epitaxy system. In this we have the two pumps. One is titanium sublimation pump and the turbomolecular pump. Whereas in case of vapor phase epitaxy, we generally use the diffusion pumps. The drawback with the diffusion pump is they contain the oil. So oil vapors will be there if you use that diffusion pumps here. So high quality pumps will be used, that is titanium sublimation pump, and the turbomolecular pump will be used to provide the high vacuum. Once this high vacuum is created, this is the hot plate. Here you have the substrate, and this is the holder. Here your substrate is placed. Okay. So this is the heat shield, so that your wafer can be protected from the external heat. Here we have the silicon, which is source silicon, which is melted with the electron gun. Okay, here we have the electron gun. This projection is done on the silicon source, so that it can be evaporated. It will be evaporated and will give you this projection. Okay, so in this side we have the dopants, and some mechanical shutters will be there. So these shutters are generally controlled with the help of microprocessors. So depending upon your requirement and the designer requirement, these mechanical shutters will be opened and closed, so that, and after this evaporation process, these dopants will also be projected here, and then here we have the evaporated compound of silicon and dopant, silicon plus dopant. Okay, so that will be deposited over the substrate. So let us quickly read the theory for this part. This is the schematic diagram of the molecular beam system has been shown. It is a very simple diagram, and the actual molecular beam system will be much more complicated. The diagram shows the two pumps. Here we have the two pumps, first pump and the second pump. We have the two pumps which is used to create the ultra high vacuum in the process. It is impossible to achieve this ultra high vacuum with the help of this single pump. So we generally prefer to use the two pumps, and the diffusion pump and rotary pump which are used in VPE process or any other epitaxial process, that are not preferred to use in molecular beam epitaxy process, because those pumps will have some oil, and that oil will be diffused. That oil will be diffused and will be present in the form of vapors, right, in case of molecular beam system. So we generally do not use these rotatory pump and diffusion pump in case of molecular beam epitaxy. So a pump like turbomolecular pump system, cryo pump, ion sublimation pump, and will be used so that a very high vacuum can be created. Now inside you can also see the silicon source which is present on some crucible, and next we have the electron gun. Electron gun was there. The electron beam is focused on the silicon source so that the silicon will get evaporated, and in the conical shape in the another side we have the dopants which uses an effusion cell. An effusion cell is again a dopant holder which is heated, and there is a small opening at the mouth of the effusion cell which jet of evaporated dopants come out, right. Some shutters are usually controlled by microprocessor, that I have already told is used to control the layer thickness as well as the number of dopants which are incorporated in the epitaxial layer growth, right. So this point we have covered this silicon source which is present, electron gun, and this side effusion cell which contains the dopants and the mechanical shutter. So next there is a substrate holder, there is a small heater, there is a thermocouple to measure the temperature of the substrate, and the substrate temperature is usually lower around 400 to 800 degree C. So the first problem is how to maintain the ultra high vacuum, because every time you introduce the substrate inside the chamber, it will be opened and it will be exposed to the external atmosphere, right. So if your vacuum is disturbed, it is not possible to maintain the vacuum at the same level. So another important system, that is load lock system, is used in the molecular beam system. In this system, suppose we have one door or a latch with two O-rings, right. So once you place the sample inside the chamber, it will be placed in a O-ring, and again and nowadays multi-chambers are also used. So we can place the sample on this hatch and then you can turn it on, and we are turning this when we are turning this on, the vacuum will not be broken and the sample goes on the other side. Okay, so the next O-ring will be free to accept the sample. Next sample will be introduced into the chamber. We may have multi-chambered system. In fact, most of the MBE system will have more than one chamber. Next is the cleaning. The cleaning is the very much important part in case of molecular beam epitaxy, and it should be in situ cleaning, that is the cleaning of wafer inside the chamber. So before the epitaxial growth, there must be a provision for the in situ cleaning. otherwise we are going to have a lot of defects on the epitaxy layer. So one method is bake the wafer. So the first method is bake the wafer at a high temperature at up to around 1000 degrees C to 1200 degrees C. And the another is we can sputter some gas on the wafer that will clean the contamination present on the wafer. So focus that low energy beam of the inert gas, generally argon, is used to the surface and you are sputtering the surface so that can be cleaned, and that is you are physically removing the thin layer. But the drawback with this sputtering is usually the argon gas is an inert gas which is used as a argon beam for the sputtering process. The drawback is it may give you some dislocation, but generally we prefer to have this method. Sputtering is used, we can manage the sputtering, we can heat up the wafer so that dislocations can be taken care. Instead of that, bake the wafer at high temperature, because if you bake the wafer at high temperature, we are going to surrender some of the advantages of molecular beam epitaxy. Next is rapid thermal process. The chemical and physical process applied to silicon wafers are generally thermally active, and typical silicon based process use the batch furnaces for the thermal fabrication steps, and the batch consists of 20 to 100 wafers per batch. Okay, so a batch of process will be there. When you have a batch of process, the thermal condition should be maintained. The process of wafer required tight control of contamination of process parameter, reduced manufacturing cost, and some producers are now using the single wafer processing steps in some step. So these are the furnaces which are used for thermal processing, rapid thermal processing. We have this quartz window, wafer will be placed here. This is IR pyrometer. Some lamps will be there, reflectors will be there. From this side we can have inert gas so that cleaning can be done. And this is the batch furnace system where you can use n number of wafers. In this case we are using a single wafer. Here in the case of batch furnace system, we can have n number of system. And this is the diagram for continuous heating source vertical furnace used for rapid thermal process system. In this we have the heater module. This is the heater module, the heating section, some lamp type heating section will be there. These are the heating elements. This is known as the process chamber. Then insulator will be there, wafer is placed here, and transfer chamber from where we can place the wafer. From this side gases can be passed in, and from this side your wafer can be unloaded. Okay, so we have this complete system is mounted on an elevator. So the most important feature of this rapid thermal annealing process system is that it consists of tungsten halogen lamp. Tungsten halogen lamp, which is used for the quick delivery of radiant energy to the wafer with the wavelength of 0.324 micrometer. Because of the optical characteristics and the wavelength of the energy transfer, the quartz wall, the wall of the chamber do not absorb the light efficiently, whereas the silicon wafer will absorb the light. And the reduction in temperature exposure afforded by RTP is the one dramatic point. However, the rapid heating with a large temperature gradients can cause the wafer damage in the form of slip dislocations introduced by thermal stress, and heating can be non-uniform across the wafer because the process is carried out at high temperature, high heating, and the large heating duration is there. So there will be thermal stress, and dislocations will be there. On the another side, convectional furnace process brings with them a significant problem such as particle generation from hot walls, because we know that if you use hot wall chambers, the contaminations, the chances are contaminations will be deposited on the epitaxial layer. So, limited ambient control in open system is there. The large thermal mass that restricts the controlled heating time, that is tens of minutes, and the requirement of contamination process control, cost and the space are driving a paradigm shift to the RTP. This RTP process demands on the growth of high purity. This system is very much in demand to grow the high purity epitaxial silicon layer, which include the ambient purity. Ambient purity means no oxygen precipitates will be there, no water concentration will be there, and the contamination per billion particle range is very much less in case of RTP, this rapid thermal process. And the gas flow pattern can also be controlled, minimize wall deposition will be there, and vacuum capability, that we have to maintain the vacuum throughout the process. So, in today's lecture we have covered the comparison between vapor phase epitaxy and molecular beam epitaxy, how the molecular beam epitaxy is used to overcome the drawbacks of vapor phase epitaxy, what is the basic chamber that is used for this molecular beam epitaxial growth system, and another is rapid thermal process system, because we are using multiple wafers on a for a single batch, multiple wafers are used. So, how that rapid thermal process can be carried out. Thank you for listening.